Hi, everyone. Welcome to the afternoon sessions. So we're going to hear from Chloe Mirzayi, who is at CUNY Graduate School of Public Health and Health Policy, works also with Levi Waldron, and the topic is Epidemiology for Bioinformaticians. If you're on the virtual platform, please put your questions into the Q&A, and I will raise them during. And if you're in the room, please feel free to raise your hand during the demo.
Good afternoon, everyone. Thank you for that great introduction, and thank you all for being here instead of at Vince's Python talk. I know that's very tempting. So we need to make them jealous, though. So every joke I make, a few, please just laugh as loud as you can, so they hear it across the hall, and really make them wish they had come to my talk. So, what? Sorry. Yeah. So I'll get started. So it's going to go very fast because usually I give this talk in like an hour and a half. So we're going to go really quickly. But you might be wondering, who am I? My name is Chloe Mirzayi. I'm a data scientist at the same University of New York School of Public Health. I work with Levi Waldron. I have a PhD in epidemiology as of 2 months ago. So that's exciting. I get to brag about that for at least a couple more months, right? And I work on a variety of epidemiological studies, everything from, very case control, cohort, and RCTs. So I wanted to bring some of my perspectives from the epidemiology world to bioconductor, as I found that a lot of people don't have a lot of exposure. In fact, let me poll the room real quick. Who here has taken an epidemiology course? Okay, I see 3.5, kind of. Oh,
You can keep going.
Okay.
I'm going to try to fix something.
Okay. So I think, yeah, we in bioinformatics have a lot of exposure to biostatistics, to biology, and to a lot of other disciplines, and we work kind of related. Oh, is it just sizing?
They were seeing the presenter mode.
Oh,
sorry to interrupt. You can keep going. I'll just try to fix this.
We could also set it to mirrored. If I don't have notes in there.
I'm just going to try to share the full screen or window.
I'm going to be switching through a bunch though, but for now, that's fine.
So it would be better to do full screen.
Yeah.
Okay, then let's turn off
presenter. Yeah. We can. Sorry, everyone.
Sorry about that. They
No
just
worries.
couldn't. The online people couldn't see the full. Okay, so
yeah, I think you do that.
Share screen, full screen, and then just do
turn off presenter mode.
Yep. Okay. Sorry for the interruption.
No worries. Use presenter view off. Okay. Perfect. Okay. And there are my cats, by the way. You're going to see them a couple of times. So the expectations, this is going to be a very quick 45-minute whirlwind introduction to fundamental concepts of epi. I'm going to try and give you what like an epidemiology student would learn in 4 or 5 classes in 45 minutes. So we're going to go through a lot. I'm not going to cover a lot of the kind of math underlying it. If you want to do the math, talk to me after. I can send you the books and you can look at formula to your heart's content. But feel free to ask questions whenever. Put up a hand, shout at me, hey you, whatever you want to say. Just get my attention, because I want this to be a conversation. I think we're all working as researchers or scientists in some capacity. And people have said some really cool stuff when I've given this talk before. So feel free, to share questions, experiences, comments, thoughts, whatever comes to mind. And yeah, so I'll start with some fundamental concepts of causal inference. I'll discuss DAGs, which are a way for us to visualize our assumptions when we are doing a research study, explore concepts of bias and confounding that are relevant to research, review some common study designs and the implications for causal inference. And then, if we have a moment, we'll talk about tools in R that can help with causal inference. I'm going to stay in these slides for just a couple more, and then we'll switch over and start kind of working on things together. And so you've got a few options here, depending on how you want to engage with this talk. If you want to follow along with it, you can use the workshop.bioconductor.org link and launch the project, or you can just look at the kind of compiled notes that I've put together that are on RPubs, Or, I know it's after lunch. Maybe you want to rest your eyes. You can just, I won't say anything if you just want to close your eyes for a bit. I understand. Cool. So we'll get started. So the classic epidemiology problem is smoking and lung cancer. We all are pretty sure these days that smoking causes lung cancer, right? But in the 1950s, 1960s, this was pretty controversial. And in fact, the statistician R.A. Fisher, who I think a lot of us probably know, but if you don't know, the F distribution, ANOVA, null hypothesis, pretty much anything. If you're ever in like a statistics trivia competition and you need a guess, just write in R.A. Fisher because he's probably involved in some way. So he's this very famous statistician, but he thought smoking absolutely did not cause lung cancer. And he wrote tons of articles, spoke at conferences. I think there were even some evidence that he like meddled and stopped the publication of some articles. Like he was really against this as an idea. And so I want to ask you all a question. People can try to answer. You can mull on this. If you wanted to prove Fisher wrong and say, no, smoking does cause lung cancer, how would you do so?
Mice and then a controlled experiment.
Okay. And then what if R.A. Fisher comes back and says, well, that's mice. Those aren't humans. Those are completely different. They're animals, not people. What would you do then?
Well, I think I would argue that it's probably still, if he would need to explain what's the big difference of it causes lung cancer in mice, why that wouldn't be the case in human, and just saying like they're small and we're bigger or something, I wouldn't be convinced by.
Okay.
But yeah.
No, that's a great idea. Yeah, an animal model.
So I also have some kind of similar discussion with my roommate like many years before. If I ever doing this experiment, I will find a group of smokers, and then because it's kind of unethical to ask them to smoke. So I will start with smokers, and then half of them I will ask them to stop smoking.
Okay.
And then see follow them for maybe 5 years, and then see the rate of lung cancer.
And that's a really great experiment, like a smoking cessation experiment where you encourage people to stop smoking. Although I think R.A. Fisher would probably respond and say like, oh, well, how do you know they actually stop smoking? Maybe your two groups are polluted. Some of the people in the control group stop smoking and some of the people in the case group didn't stop smoking. So how do you know the difference? How can you be sure?
Guess like the Fisher has a power calculation, right?
Yeah.
I just guess. I don't know who developed power calculation.
I mean, it's a good guess. I have no idea. Yeah. So I mean, and the fundamental problem was that Fisher could not be convinced, and he argued that there was some underlying genetic factor that both increased the probability of people smoking. Maybe it made smoking more appealing, or made the taste of tobacco smoke taste better for these people. And then that genetic factor was also causing lung cancer, which we do know actually now that there are factors that influence whether a person starts smoking, but it doesn't explain, the correlation we see between smoking and lung cancer. So, classic example. So we'll be coming back to this because this is like how modern epi emerged. And so I think the question that emerges from what we just discussed is, what does it mean to cause something? You hear this statement, correlation does not equal causation all the time. So what does it mean to cause something? Does anyone have any ideas? And I know this is like a freshman year philosophy class, like, I don't know, see out on the quad, like, dude, what does it mean to cause something? But like, anyone have any thoughts? Yeah. That's perfect. Awesome. Like a counterfactual. If X had not occurred the way it did, maybe Y would differently or not at all. Awesome. Yeah, that's actually my next slide, the counterfactual definition of a cause. What would have happened had the event of interest, or that should be in parentheses, the exposure had not occurred. And I like to think of a very practical example. I live in New York City, so there's a lot of noise at night. And so, like, did an ambulance driving by cause my dog to start barking? And then that's kind of the basic question, but then we can reframe that as a counterfactual question. Would my dog have barked if there had been no ambulance driving by? And then we can apply that to concepts of health. So we can say, does smoking cause lung cancer? And reframe that, would a smoker still have developed lung cancer if they didn't smoke? And, a big controversy in some political circles was, does the COVID-19 vaccine increase the risk of, let's just say, blood clots, not lung cancer? And the way to reframe that would be, would people have developed blood clots if they had not been given the vaccine? And does anyone want to throw out an example from your own research or something you're thinking about? No thoughts? Fair enough.
I mean, I guess I'll do.
Yeah.
So we study GWAS loci, and so we know that like somewhere in this region, variants are associated with, say, like diabetes incidence, and we want to know if we identify a gene whose expression is like the cause.
Yeah.
We know there's an association, but we don't know the mechanism.
Right. That's a classic example where GWAS identifies a lot of associations, and then you need to actually figure out which of those are potentially causal. So, yeah, great example. Any other thoughts? If not, I'll keep going. So I'm going to switch gears. So this is kind of the wordy definition, but we can start thinking about causality kind of in a diagram, because I find this, this counterfactual definition is not always the most intuitive. You have to kind of think philosophically about this, multiverse where something happened, didn't happen. This isn't a Spider-Man movie, so maybe we want to just make a diagram, right? So we can make what's called a DAG, or sometimes you'll see them called a causal graph. And, we love visualization. So how can we visualize this? Well, we see on the bottom here, we've got smoking, our exposure, we've got an arrow pointing to lung cancer. So this is a theoretical model that smoking causes lung cancer. This is the simplest form of a DAG, because we've only got two variables and one relationship, but they can get pretty complicated pretty quickly. And so what we want to do is make some DAGs. So let me teach you how to do that. And it's often, when I start my research, I always start by saying, what is the relationship I'm interested in here? And I start drawing the DAG. And I think it's a great way to start when you are formulating your research question. So we will exit out of PowerPoint. And I'm going to start by showing you a kind of a software on the internet called Dagitty, dagitty.net. And let me go to the homepage and you guys can see this. And this is a great little tool for making DAGs. So you can just hit launch here. You'll get this basic model that they've put together here, which is, just an example model, but we can make our own model by going to the top here, say model, new model. And we get this blank canvas for us to work on. And let's start with something simple. So we'll start with our smoking. You just click anywhere on the screen, name a new variable, smoking. I apologize for the people watching at home because my camera is down below, so you are seeing my fingertips right now. I hope they are clean. We'll add a second variable called lung cancer. So we've got our two variables with no relationship between them. We can just click on both of the variables. We've got our theorized causal model here. And we can specify by clicking on the variable and then clicking that this is our exposure, and then clicking on lung cancer and clicking that this is our outcome. So again, this is very simple. Let's make it more fun. So we can add what R.A. Fisher said, that there was some kind of genetic variant, and we can show the relationship that he was interested. So he argued that this was the real relationship between smoking and lung cancer, that there was this third lurking genetic variant that they couldn't identify, and that explained all the correlation between the two. But we can think of an observational study, maybe of smoking and lung cancer, doing an RCT of smoking and lung cancer would probably be a little unethical. But we can think of some other variables that might influence this, right? Like age. And that probably influences someone's smoking behaviors or some kind of measure of lifetime smoking. We can add other variables. I think we could probably just do like an SES variable. It's up to you how detailed, how many variables you want to go into. Yep. Socioeconomic status. Sorry, that's like a very epi term, I guess. Yeah, so just like race, income, education, bundled all together. You could separate them out if you wanted to. And I'd like to note that these pathways, you know, they don't have to be direct. Like there can be a lot of variables that you're implying kind of lie on this pathway. So like, you know, obviously smoking does not directly cause lung cancer, but it changes, you know, some cellular structure, which then encourages tumor growth. So there's a lot of little variables that lie on that pathway. So you don't have to, there can be lots of mediators going on in the pathways, and you don't have to have all of them in here. That pathway implies that there are variables present. So we made this nice, well, maybe I'll move this around a bit so you can kind of see the names better. We've made this nice little DAG. That's nice and all, but we're here to talk about R, right? So like, let's go to R. So we can take this model code over here, copy it. Let's go to R. I'm just going to make a new script so I can kind of show this. There's this great package called dagitty. And we can just say dagitty, and then just paste our model code in there, and then wrap this in a plot. There we go. So we just went from, you know, playing around with it and everything's in the same place. It's really nice because you don't have to worry about figuring out all the positions of things. You can adjust it yourself, and then, you know, just put it right into R, and quite publication ready, but you can play around with it. And there's even better. There's a package that builds on top of this called ggdag, which brings a ggplot2 style nomenclature to dagitty. So let me just save this object right here. Let's call this smoking. Dagitty causes smoking. Yeah, because of the arrow. And you can say, I think it's just smoking. And we'll put a theme. Yeah, theme dag. Where that gets me. Did I miss something? I probably missed something. Let me double check my code. Should just work. Oh, maybe I didn't. The one in here is working. Maybe I just need to set these. I don't think I need to do that, but live coding. Yeah. Yeah, restart the R session. Any questions so far while we wait?
When you're thinking of all these other things as you build your initial day, I know as you get further along, it gets more complicated.
Right.
Like, you put all of the factors that could potentially affect the outcome, or do you just like tailor it for things that you think are more likely than not to be impacting the question?
That's a good question. So when I'm making a DAG, I like to start with like a kitchen sink approach where I just throw everything in there that I think is probably relevant based on my, you know, knowledge of the subject matter or what I found in my literature review. And usually you end up with this big complicated thing and probably half the variables you don't have a measurement for in whatever data set that you're probably going to be working with, or that's not really those data if you're using this to plan a study. So, and then you kind of like think about, okay, well, what's important here? What proxies do I have for this? And then I make changes. So it's a bit of an iterative process. I usually narrow it down as I'm presenting it, and then I will, kind of keep the original and keep that in mind when I'm presenting my results and say like, well, I really would have loved to have these other variables, which I think are important to this relationship. I don't have them right now. So everything should be interpreted in light of not having those data. So yeah, that's an excellent question. And I think there isn't really a wrong way to do it. The epi kind of state of the art right now is just encouraging people to do it, to even just try it, because I think if you look at a lot of published epidemiological research right now, people don't really talk about why they chose the variables that they did, or where they're coming from, or why they theorized that these variables were important. And the goal is to start thinking about that and to think about what causal structure do I think is at play here that I'm interested in. Because in the end, our goal, hopefully most of the time, is to go from association to causation, right? Like even, and I got into a debate about this at a conference a few months ago, but in my mind, there's like 3 types of studies. There's descriptive, predictive, and causal. And you're doing one of those 3 when you do a research study, whether you know it or not, and whether you like it or not. So, and often, a lot of research where if you are adjusting for variables, you are probably trying to theorize some causal mechanism, whether you know it or not. So, good question. A debate that with me, I'm happy to talk after. So let's see if that works. There we go. Yeah, restarting R did it. So we get this graph. You can see things stay in the right position. You can play around, make it nice and pretty, just like any GG plot. And there's just a lot of options, and it will be very familiar. Mostly, it's not quite the same as GG plot 2, but it's pretty close. So yeah, this is how we make DAGs. I made all my DAGs for my dissertation using this. So any questions about making DAGs?
Well, I'll ask one.
Yeah.
In your on the dagitty website, there was an interesting stuff on the top right, talking about. I don't know if you're going to get to that.
I'm about to get to that. That's such a good question.
I didn't look ahead.
People are being really good about asking the question that then, or making a comment that leads into the next thing. I'm so pumped that you guys are like on this. This is exciting. So that's a great question. So you notice that there were those lurking third variables in here, right? These genetic variants, the age, the socioeconomic status, and those variables could be introducing bias, right? So what are those variables? Does anyone know the name for them? Confounding. So I think, this used to not be, we just used to think confounders were something that we could just, I don't know, they were just something that was associated with the outcome and the exposure. But there is actually a formal definition of a confounder, which is something that has a causal relationship with the outcome, and it has to cause the outcome. It causes the exposure, and it's not a mediator. And again, I'm summarizing. There's a lot of math kind of proving this point. And if you want, I will mention the book at the end that you can go to see all the math that proves what a confounder is and why it biases relationships. And so, this is that example I was talking about with the ambulance and the dog barking. So we could imagine that there could be a lurking confounder that caused my dog to bark, which was a car crash that happened. And maybe the noise of that car crash is actually what started my dog barking. But if maybe I didn't wake up until I heard the ambulance, I would erroneously conclude that the ambulance is what caused my dog to start barking. So that's a confounder. And so my question for you is, what are some common confounders in your research? I think there's a big one in bioinformatics that people talk about. Any ideas? Yeah.
Randomness or the batch effect?
Batch effects, perfect. Yeah, batch effects, very common. It might not always be a confounder. It kind of varies. Sometimes though, if the cases and controls were sampled in different ways or different methods or done on different days, that could introduce a batch effect. And that could be, if you draw out the DAG, could be, you end up inducing a causal relationship on accident.
So I often say like your batch and your condition are confounded.
Yeah.
But that's it's kind of like, is it stretching the meaning of the word in this context, because the batch isn't causing the condition?
Right. So it could be the opposite, where the condition is causing the batch, and that in that case, I think that would be the next thing we're going to talk about, which is a collider, which could induce a different form of bias, but could still introduce bias. So controlling for it is still actually kind of the correct thing to do.
I guess like in this situation where someone just happened, like they thought it would be the right way to set up the experiment. They just happened to put all the treated samples on day 2.
Yeah.
So like someone's decision caused both of these variables to be perfectly correlated.
Yeah. And I mean, and you could add that to the, like, we've been doing very simple DAG, but you could add those variables, like the person's decision to assign it to this trait. You could add that as a variable and then think about how that affects the causal relationship that you are hopefully investigating. Yeah, so batch effects is the big one. I mentioned some common ones: age, everyone adjusts for age, socioeconomic variables. Sometimes you'll adjust for different, disease severity. Although that one kind of depends, I think, whether it's actually a confounder. And so there's also this idea of unmeasured confounding, which is a big issue in any kind of observational study. We can't collect data on every single possible variable, and there's probably ones we don't know about. And so we can't really deconfound or control for a confounder that we haven't measured. There are methods that try to do that using some kind of statistical tricks or sensitivity analyses to say, like, how vulnerable is the result I'm seeing to kind of an unmeasured confounder. But in the end, it's a missing data problem. And if it's missing data, there's only so much we can do. So the other kind of big thing you'll see in a DAG is what's called a collider. And this looks like a confounder, but in fact, the arrows are pointing the opposite direction. So instead of the confounder causing the exposure and causing the outcome, the confounder is now, or the collider is being caused by the exposure and the outcome. And I just want to belabor this point that they are not the same thing. And if you adjust for a collider, you may actually introduce some bias where there wasn't some before. And we'll discuss why that is in just a moment. But again, using my example here of the ambulance and the dog barking, we could imagine sleep disruption as a collider. So both the noise of the ambulance and the dog barking causes sleep disruption. But if I tried, if I was looking at a study of people who were sleep deprived due to ambulance and dog barking, I don't know, if I only selected people who reported not having sleep disruption, then I might not have any data at all, because maybe there was no ambulance or no dog barking at all. So you have to think about, what this collider might be doing to your data. And yeah, so adjusting for collider as one would a confounder will create bias, potentially. And the reason why is because it opens what's called a backdoor pathway. I won't go into too much detail about what that is because we only have like 10 minutes left. But there's a pathway between the variables. There's the direct pathway, and then there's kind of this indirect pathway. And that pathway is unblocked when you adjust for the confounder. Or adjust for the collider, sorry. So the major source, the major type of accidentally conditioning or adjusting for a collider that happens is selection bias, which is something we do on accident. It's not something you usually do on purpose. Usually something happens. So classic example of selection bias. So I'll start with this. Does anyone recognize this? Someone want to explain it? Go for it.
Initially thought these are the areas where planes World War II came out of getting hit, therefore we need to armor those. Actually, those are because it was from planes returning, those were the ones that got hit and could still make it back to land. The places that appeared to not be getting hit were the ones that were shot down.
Exactly. So this is an example. You hear it called survivorship bias or survival bias, which is all just a form of selection bias. It just means something has caused some form of selection that results in the people who've lived long enough or are able to participate in your study. They're different than the people, the total population of people that you wanted to have in your study. And so this is, and you'll see this on the internet as like a meme sometimes, but this is a classic example of selection bias, the World War II planes. The other example that you hear about a lot is the healthy worker bias. And this came up a lot in occupational studies of coal miners. So a lot of coal mines were arguing that, our workers don't get sick from the coal mines. Look, all our workers are healthy. We did a study, all the workers who've been here a long time, none of them are sick. And the reason, and so the sick ones left the job, right? And so that is another example of what's called the healthy worker bias, which is just a type of selection bias. But you'll find that selection bias comes up a lot. It comes up in cancer studies as well. Generally, people with very aggressive forms of cancer may not live long enough to be in your study. So you have to consider when you are collecting data, any type of condition where people may not be able to participate. And it can be fairly broad. I mean, one of the faculty I work with was working with UK Biobank data, and even that, she was able to prove that there was some selection bias just because the people who survived long enough to give samples to the UK Biobank are different from people who die, at a very young age and don't participate in that. Cool, so that's selection bias. And in that case, you've inadvertently conditioned on a collider, you've introduced bias. The hard thing about this is, if you've done this, it's really difficult because you've selected for people, and therefore the people you should have selected but didn't are not in your study. And so the question I often get is like, what do I do if I think there's selection bias? And I think, again, the best thing is probably some form of sensitivity analysis to try and imagine, how, if the selection bias is very severe, how does that change the relationships that I'm observing? So real quick, in the last few minutes, we're just going to go through a few different study designs and talk about what those actually look like from a DAG, and you can think about this. So first up, RCTs, we're all pretty familiar with these, but here's what a DAG for an RCT would look like. So you have some kind of randomizer, that assigns an exposure to the participant, and then we follow them to see if they develop the outcome. And in that case, can there be any confounders if you did it right? Think about it. It shouldn't matter what your starting population was, right? It's randomized. Nothing can cause the exposure if you assign them the exposure, if you did it properly. Like if you I don't know, somehow messed up, your random number generator failed somehow, or some cases in multi-site studies where maybe they had one site that was a case site and one site that was a control site, but the sites differed in some way. But assuming that they're truly random, nothing can confound this relationship. And that's what's so powerful, because we don't have any potential unmeasured confounders. And so assuming that there's no selection bias, what we should observe between exposure and outcome is a true estimate of the causal effect of the exposure and the outcome. Now, where could selection bias occur in an RCT? Perfect. Lost the follow-up. Yes. Like that's the biggest source of selection bias in RCT is participants, maybe they have got bad side effects from the medication, or maybe they're not compliant with, whatever the treatment is, and they drop out of the study and you don't have their data anymore. So that can be selection bias. Yeah, perfect. So even though we don't have to worry about confounding, still have to worry about selection bias. And then I talk, we've got like 5 minutes left. So I talk about some other study designs in here. Cohort studies are another kind of big one. They're the ones that I am mostly involved with. These are types of observational studies along with case control studies. And in these, the big issue is there can be both confounding and selection bias. A GWAS, which we talked about a moment ago, that is still an observational study, and there can still be potentially confounding, actually. And so that's something you have to worry about, even if you're working with genetic data. And so since I only have like a few minutes left, I do give some more examples. I create this very slightly more complicated DAG, and then I present some code on how we can identify what we need to adjust for without having to sit there and trace the paths and figure out what's a confounder. You can just do it in R, and R will tell you if you want to identify the effect of X on Y, here's what you need to adjust for. And we can actually visualize that. This is a little squished, but you can visualize that in ggdag. You can tell it ggdag adjustment set, and it will say, here's what you need to adjust for to find the effect of X on Y. And it gives you 4 possible sets of control variables, because this is a pretty complicated relationship. So no need to actually figure out what anything in your DAG is pointing to. Once you've made it, you can just ask R to figure it out for you, which is great when you have a very complicated DAG. And then I just show some examples in a few different packages that I'm familiar with about how you can adjust for confounders. And I show a quick example of adjusting in curated and metagenomic data using DESeq2. But I make the DAG, and then we find the variables we need to adjust for, and then we adjust for them. I've got 2 minutes left, so I want to open up the floor to any questions in these last couple minutes. Yeah.
This last bit. So you include this regular kind of variables in the design formula.
Yeah.
When would you include it as an interaction term?
That's a good question. So an interaction term, generally speaking, is when you're in a causal model, would be when you're looking for effect measure modification, otherwise known as moderation, but epidemiologists have been calling it effect measure modification now. So whether you're looking to see if there's like an additive or multiplicative effect of the two variables, which you can have variables that are both confounders and moderators. Again, that's a little advanced for this 45-minute workshop, but if you're interested in that, I can recommend some resources.
But it would be also another way of, that would be another kind of arrow type, I guess.
So there isn't really a good way to represent a moderator on a DAG because what is a moderator what is like the causal mechanism for a moderator, right? We're hypothesizing that the interaction of two variables has a synergistic or I guess antagonistic effect where they either increase the overall effect or decrease it in some way. And you can't really, I don't know if there's a great way to represent that on a DAG.
Arrow pointing at another arrow.
Arrow pointing at another. Yeah, I've seen that before. I know that that's controversial though, from what I understand. Yeah.
So in my study, actually, I'm also using the social determinant of health variables to as a confounder to my study. So I wonder, the issue here is that I have too many variables. There are about 600 variables in my data.
Yeah.
So I'm thinking about, is there any way to automatically generate this kind of tag for me? Because I don't want to evaluate them one by one to make this.
I don't know that there's, because it's supposed to be driven by your theoretical approach. I don't know. I mean, I think you could probably feed in just your list of variables and start there and maybe whittle down. But yeah, I don't know if there's a way to automatically do it. But I mean, if you're, yeah.
And is it a good idea to adjust for 600 variables confounders?
I mean, at that point, you're running into dimensionality problems depending on how big your data set is. So there's other techniques. You could use some kind of dimension reduction or inverse probability censoring weighting, something like that. or treatment weighting, not censoring weighting. Yeah. Any other questions? Yeah.
So I noticed you had the million randomization up there. As,
Yeah.
like, we think of that as like a randomized clinical trial, right? Where
Right.
the variant is the randomization factor.
Correct.
So one thing I've been struggling with is with the emphasis on getting multiple ancestries and into a data set, right? Like we know that your genetic variant are loosely related to race, which impacts like how you're treated and your access to resources. So I'm always confused about how that interpretation of randomization holds up when we're looking at things like access to healthcare and other social determinants of health.
Yeah, I mean that's it. So it's sometimes called like a pseudo-random study in epidemiology. You'll see that these studies that do similar, they try and do something similar to Mendelian randomization, where they find some kind of randomizer, like they'll say like distance to the hospital maybe affects whether people seek treatment, or they'll look at different states who took up the Medicaid expansion and treat that as a randomizer. But yeah, there's a lot of cases where it probably isn't quite as good a randomizer, I think is what you're getting at, that there's probably some confounding there that you can think about. So it is a good point to think about when we are using any, and that method writ large is called an instrumental variable approach. And we have to think about our instrument and whether it is in fact truly random. Did that? Yeah, okay. Thanks. And just since we're 2 minutes over, I just want to mention, if you want to learn more about this and you just want like a really easy primer, there's a book called The Book of Why, The New Science of Causal Effect by Pearl and Mackenzie. Pearl is a computer scientist and most of his academic writing is very difficult, but he wrote this book as kind of a mass market book with a journalist. It is a great introduction. If you want something that's a little more going into the math, there's this excellent free book by Miguel Hernan called Causal Inference What If, that comes with R code, and you can play with it and have fun with it. And then finally, if you really are hardcore and you want to see like all the math, Pearl wrote a book called Causality, Models, Reasoning, and Inference. That is like a hardcore computer scientist textbook. But if you are a bit of a masochist, you can check that out. So thank you all so much for coming and listening to my talk.